example, here is Gay-Lussac's law, and this, as you notice, relates pressure and temperature. It looks just like Charles' law, except now I'm looking at pressure instead of volume and that relationship with temperature. Okay, notice again, pressure and temperature, just like for Charles' law, they are directly related. So when pressure goes up, temperature goes up. When pressure goes down, temperature goes down. And that makes sense if you look here. If you take gas and you have it under, for example, 200 Kelvin at a pressure of 1 atmosphere, if you increase that temperature, those molecules, those gas molecules, are going to start moving much more quickly. And as they're moving more quickly because you've increased the temperature, the force with which they hit the walls of that container, that's going to increase, which is going to increase the pressure. So once again, just like in Charles's law, you need your units of temperature to be in Kelvin. Okay? So let's look at an example. It says a gas system has an initial pressure and temperature of 12 atmospheres and 27.9 degrees Celsius. If the pressure changes to 3.74 atmospheres, what is the resultant temperature? All right, so my pressure is 12 atmospheres. Okay, so I'm going to plug in 12 atmospheres. My temperature is 27.9 degrees Celsius. I've got to add 273 to that to get that into Kelvin. So it's going to be 300.9 Kelvin. That equals 3.74 atmospheres over my T2. Notice my units for pressure can be whatever I want, but they have to be the same on both sides. So in this case, they're both atmospheres. If they were both millimeters of mercury or they were both kilopascals, that would be perfectly fine. I'm going to cross multiply, so I have 12.0 times T2 equals 300.9 times 3.74. I'm going to divide both sides by 12.0 to get my T2, okay? And what I end up getting is 93.8 Kelvin, okay? Now, if I had asked you what would the temperature be in Celsius, this is a problem that really messes students up because they immediately say, well, if the answer has to be in Celsius, then I can just keep all of my work in Celsius, and that's not the case. You always have to convert to Kelvin, but then at this point, right when I'm done, then in order to get back into Celsius, you would have to subtract by 273 to get your answer. Okay? And that's it. Just always make sure when you're using your gas laws that you're in Kelvin and you're not in Celsius. So if I ask for it in Celsius, then I would subtract 273, okay? And my answer would be negative 179 degrees Celsius, and it would be that because 273 has no decimal places. So I would round this so it has no decimal places. So that makes it negative 179. Your last gas law is the combined gas law. And if you notice, it takes all the gas laws that we looked at and combines them together. Keep in mind, if you notice, you can get every single one of the gas laws we've talked about from the combined gas law. So for example, if your temperature stays constant, meaning you're going to ignore T1 and T2 because it stays the same, you've got Boyle's law, P1V1 equals P2V2, which shows that pressure and volume are inversely related. If instead I kept pressure the same, then I would have Charles's law, V1 over T1 equals V2 over T2, showing that volume and temperature are directly related. And then finally, if my volume stays the same, I've got Gay-Lussac's law, P1 over T1 equals P2 over T2, showing that pressure and temperature are directly related as well. However, if all three of these variables change, then I need to use the combined gas law. So let's look at it. In this problem, it says a child has a toy balloon with a volume of 1.80 liters. The temperature of the balloon when it was filled was 20 degrees Celsius and the pressure was 1 atmosphere. So I've got three variables now. Let's make sure all three of those change. If the child were to let the balloon go and it rose 3 kilometers, extra information that you don't need to know. We don't really need to know how high up it goes. But notice the pressure changes to 0.667, so we know my pressure has changed. The temperature goes from 20 degrees Celsius to negative 10 degrees Celsius. There's my second variable that has changed. What is the new volume? So all three variables are going to change. Therefore, I know I need to use my combined gas law. So I'm going to use P1V1 over T1 equals P2V2 over T2. And I'm going to plug in all the values that I know. So I know my initial pressure is 1 atmosphere. I know my initial volume is 1.80 liters. Okay? I'm going to put that over my 20 degrees Celsius. But remember, the 20 degrees Celsius have to be in Kelvin. So I'm going to add 273 to that, which gives me 293. I'm going to set that equal to my new pressure, which is 0.667, times V2, because that's what I'm solving for. And I'm going to put that over my negative 10 degrees Celsius, which is my new temperature, but I got to add that to 273. So that's going to give me 263. So I'm going to cross multiply. So it'd be 1.00 times 1.08 times 263 equals 293 times 0.667 times V2. I'm going to divide both sides by 293, and I'm going to divide by 0.667. And what I end up getting for my V2 is 2.42 liters. Notice I have three significant figures because my volume and pressure both have 3 sig figs each. My temperatures, when I add 273 to them, they both have 3 sig figs. Notice my units for volume were in liters, and therefore my new volume is also going to be in liters. So those are the last 3 gas laws that we're going to be looking at. Okay? We have one more that we need to look at, but that is going to relate pressure, volume, number of moles, and temperature. That is your ideal gas law. But these 4 gas laws that you've looked at allow you to compare what happens to variables when you change, for example, pressure, when you change volume, or when you change temperature.